Hi. Today we'll be actually finishing up this part of matter and measurement, the matter portion. To get started, we're going to have a quick do now. Like I said, just like last time, if you want to answer these yourself, hit the pause button, take whatever time you need, but I'll only give you a few seconds here. So, an example of a physical change. The way I like to identify the physical changes, there's two ways. One, I try and get rid of the ones that are chemical changes, or two, look for certain keywords. So we said before that phase changes are physical changes. And so that's like melting, boiling, or freezing, so that's going to point us straight to C. But also like, burning, digesting, corroding, and baking. These are all, chemical changes. They create some new matter, some new compounds. Which of these terms refers to matter that could be heterogeneous? And heterogeneous, of course, points to heterogeneous versus homogeneous, which is a mixture. All the other ones, remember, elements and compounds are pure, so they do look the same throughout their substances. And a solution is, well, homogeneous by definition. So for today, I kind of wanted to play a video. It's a little bit on the longer side, but it's entertaining nonetheless. I just want you to watch the video and write down any thoughts or questions that you have as the video happens.
We're going to be looking at alcohol today, and in particular ethanol, because ethanol is the alcohol that most of us are most interested in. It's Martin. How was the filming, Martin? It's only just begun.
This is a model of ethanol, 2 carbons, 5 hydrogens here, oxygen here, and another hydrogen there. Most people are familiar with alcohol because of alcoholic drinks.
One of my colleagues at my old university did point out it looked a bit like a dog shape. So although hair of the dog is an English term referring to an alcoholic drink you'd drink in order to combat a hangover, it doesn't come from the shape of the molecule.
Beer, wine, all sorts of things like vodka.
Is he having a drink?
These are all made by fermentation of some natural material, maybe juice from some sort of fruit like a grape or some sort of grain, wheat, barley, and so on.
Today what we're going to do with all these different alcoholic drinks is actually distill them. So the process of distillation will actually purify these alcoholic drinks. It will mean that we can actually get as close to pure alcohol as we can.
Alcohol has been terribly important in human history because in the days before people discovered how to purify water, they used to drink weak beer where the alcohol killed most of the bacteria and so they could drink safely. In Asia, people used to boil water and make tea, but this wasn't discovered in Europe and the West till many, many years later.
Right, what we're going to do now is actually distill the alcohol out of a can of beer. So the beer is going to go into that large flask there. We'll connect it up to this, which is known as the still head. On top of that will be our thermometer. Alcohol vapour will collect around here, go down this arm and into this bit. Now here we've actually got some cold running water creating a jacket of coolness around the glass tube inside it. So the alcohol vapour will get condensed into a liquid. That will flow down into the receiver and into our little round bottom flask.
You can make the ethanol from all sorts of different grains, from wheat, from maize.
You can tell I don't pour pints for a living. That's ridiculous.
That is an awful pour.
You've done an awful job.
I have done a truly abysmal job. Okay, there we go. Can of beer in the flask, and now we're going to heat that up. The isomantle is now heating up, so that will actually heat up the sides and the bottom of this round bottom flask. So what's going to happen is that you've got alcohol and water inside that vessel. The water should stay in there until, if we get up to 100 degrees C, only then will it boil. But before we get to 100, the alcohol will come off first at around about 78 degrees C.
And so alcohol, when chemists are talking, is often a shorthand for ethanol.
We've got the alcohol there, which is bubbling up, forming alcohol vapour into this area here, which is the still head. So what will happen is it's coming across there as vapour, but once it hits this cold part of glass, it condenses on it, and it's trickling down, flows along the condenser. So what we're getting right at the end here, into the receiver, and then into the round bottom flask, is the alcohol from beer.
One of the problems when you distill alcohol from water is that you cannot get it 100% pure because ethanol and water form a so-called azeotrope. What distills over is 97 or 98% pure, but you can't get rid of the last 2% of water. The only way you can remove it is by adding a third material. Quite often people add benzene to it. So the alcohol that we have in the lab doesn't contain much water, but it does
Typically it's
contain
called
nasty
denatures.
things, which means that if you drink them, you could be seriously poisoned.
From this can of beer, we've managed to get about this much alcohol.
Oh, that's not very much.
So not a huge amount, but that's what we've managed to achieve on our crude distillation apparatus here. But there you go.
I can link this video below, but we've been watching this long enough. Some things that I jotted down were alcohol and water. So a lot of times when people call something alcohol, like vodka or beer or wine, it's already a mixture. There's two things present, at least. I mean, alcohol, water, and then all the other things that give it the host of flavors that we're used to. In moderation with your parents' don't drink. The word distillation came up, which I want to touch on, and the word purify was said more than once. Azeotropes are interesting. We're not going to talk about them today. So the goal of today is we're going to talk about separations of mixtures. So a mixture is able to be separated because when mixtures are made, the substances retain their properties. In other words, like if you were to make salt water still tastes salty, like salt does. It's unlike a chemical combination, like a compound, the properties completely change. And we're talking about both chemical and physical properties here. But that means if they retain their properties and those properties are different, then separation can be achieved. Like it said in the video, we go from this mixture, it's this colorful, foamy mixture, to this clear, colorless liquid. And also that the two components, alcohol and water, she said that one boils at 78 degrees Celsius and 100 degrees Celsius. So that means that if you have your container and it's got your alcohol and your water particles in it, and you heat it up and you were holding it at, say, like 80 degrees Celsius, that would mean that hypothetically a lot of the alcohol particles would be a gas above this mixture. Now they said you couldn't get 100% separation, but at least I'm saying the idea is the alcohol particles are able to leave the solution without the water leaving the solutions too. And the word purification was used. Notice that once this separation has occurred, we now have two compounds, two samples of pure substance compounds. And so the word, like I said, pure is related to substance and then is related to compound or element. And so this process of separation will take a mixture and turn it into things that are more pure. How pure? Well, it depends on the method, and it depends on the way you structure it and the substances in question. So I'm going to go through a number of methods. There's a bunch of information here. You can write it down while I'm talking. I'm going to hit the play button on this because this video is a little longer than I want it to be, but if I do this right, I'll get to it at the right point. So the first one, distillation, which was mentioned in the video, you can see the setup here. This is like your initial time, and this is some later time, so you can see that what differences occurred. You have a Bunsen burner heating up your mixture. Some portion of the mixture boils at a lower temperature, and it boils, turns into a vapor. The condenser has water running around it, which cools down without like mixing with it. And then you get your purified substance on the bottom, the one that has the lower boiling point. If you kept heating it, you'd eventually get both substances over there, but that's where you get to be like a chemist, and you get to intervene at a certain time to allow for a controlled process. It is non-destructive. If you do it correctly, you have just salt and just water at the end, or just alcohol and just water at the end, or like 98% pure or whatever. For this to work, you do need a significant difference, at least 20 to 30 degrees Celsius. Salt has a boiling point up in the thousands of degrees Celsius, I think, and water boils at 100, so that works. That said, I've only really noticed this in a liquid-liquid mixture. If you've been watching the video below, there are some lower tech versions of distillation that do accomplish the separation without maybe being as elegant. So in this case, I've made some salt water, and then I'm going to put it, that's a crucible I've turned upside down, a metal crucible, and as you can see, it's quite hot. The water's boiling off, and that white substance that's left behind, that residue, is actually the salt. So we've dissolved the salt, and we're actually now undissolving the salt by boiling off the water. That's fine, but this process really only results in me having the salt at the end, and not the water. The water is leaving and is spreading out into the room, and presumably I'm breathing a little bit of it now. So this evaporation or boiling process, it works if you're not worried about retaining your entire sample. And I'll leave it for a little bit more. It's 15 seconds. We'll zoom in and see the fun stuff, because I think it got a little too hot there. You see the water droplets are actually falling off. But let's move on. Another method is centrifugation. This you may remember from a biology class that you took. And the classic example is to take blood, which is of course a mixture we can see here, and by spinning it around really quickly, we can actually separate it based on densities. High density ends up in the bottom of the container, because the idea is as it spins around in a circle, the more dense things are shoved to the outside. Well, they're not shoved. They fail to get pulled in a circle as well. My physics teachers are going to get upset with me if I get that backwards. There's no centrifugal force, it's centripetal. But the lower density objects do end up closer to the middle of the spinning, which ends up being the top of the container. And this works anytime you have a mixture of substances that are, things like a solution might work, but really it's when you have things like colloids and suspensions, things that are kind of gummy, and this is a way to separate them. Another way to separate is filtration. Obviously, filtration works where you let something go through a filter paper. And the idea is that we're separating based on particle size or solubility. So this filter paper has little tiny pores or holes in it, and the pores let small particles through. In this case, water and dissolved substances. So when you do dissolve a salt in water, what ends up happening is those particles get broken up into atomic scale particles, sizes, which are allowed to pass through the filter, and then larger things that maybe don't dissolve in water don't. So a good example is for filtering is anytime you want to get water out of something. This is how coffee is made. The idea is the hot water passes through the coffee, and caffeine and other things dissolve into the water, and they pass through the filter, and the coffee grounds stay in the filter above. One example I have to talk about here is a salt and sand mixture. If you had salt and sand, it'd be really hard to separate them. However, if you add water, the salt would dissolve and the sand wouldn't. So hypothetically, if you had this salt-sand mixture and you added water first, this would be salt water, which we just talked about how you could separate, and this would be basically wet sand, if that were your mixture, which is interesting because you have to add a third substance to actually accomplish your separation. Chromatography is, again, something you may remember from a biology course that you've taken before. The idea is that capillary action, liquids can soak into paper, sometimes defying gravity. And this separation here is based on something we call solubility, which is, in other words, a way how well the molecules interact with certain substances. So in this example, we have a piece of paper, we have hexane, which is a liquid, and as the liquid is drawn up the paper, the pigment, the substance that you put on the paper, is going to interact with both the paper and the hexane. And basically, as the hexane passes, the more the substance is attracted to the hexane, the further it will travel with the hexane. And the more it's attracted to the paper, the more it's going to stay put. So what we can see is we have two components, x and y, and x moved more. Moving up equals soluble, or it means it has more interaction with the liquid phase. Finally, I think it would be good to talk about one method that is used a lot, you can see in real life. This is a magnetic separator. The idea is all your stuff moves down conveyor belt, and on top is a very powerful magnet, and there's something whacking things to the side. So as the magnet pulls things that are attracted to it up, the things whack it over to the side, and then the rest just passes underneath and keeps going. Ferromagnetic substances, oops, where'd my pen go? Ferromagnetic substances are substances that are attracted to magnets. And in terms of elements that are ferromagnetic, there are three that we should know about. Iron, cobalt, and nickel are the big three. They're the ones that you can actually pull out with a magnet. So if you're ever looking at a mixture that has, say, iron in it, it might be worth investigating magnetism as a method. So to quickly summarize things up, separation is possible for mixtures because physical properties of the components of the mixture are conserved when the mixture is made. And so if you are judicious about designing an experiment or designing a setup, you can effectively cause that separation to occur and get pure substances. But for that means to be able to do this, you need to know a bit about the substances that you're separating, and order can matter. So as a last word about that, I want to talk about, well, there's two things I want to talk about. No, one thing. If we had, say, a filter sitting over here, and then we had that mixture I mentioned of sand and salt. Oh, no, there are two things. And I just poured the sand and salt into the filter with the filter paper. Nothing would happen. Everything would there'd be this solid sitting up here. Yes, you could rinse it with water, but there's nothing saying that you'd actually dissolve all the salt. The smarter thing to do is to add water before filtering, and that's where I'm saying like experimental design and order can matter. That said, if there were some sort of like ferromagnetic substance in your mixture, sometimes even adding water can be dangerous. So you have to think about your substances, and the order can matter, because if iron rusts, the rust isn't magnetic. So there's these like layers to consider where you're saying, oh, if there's iron present in my sample, I have to get that out first, but I also need to add water, but I can't add water before I get the iron out. And you have to kind of think about how best to order your steps and what steps to use in order to achieve a good separation. Thanks for watching.